In this module, we want to expand the kinematics to multiple dimensions, and I'll stick to 2 dimensions in this case, though it's easily expanded to 3 once you understand the vector notation in 2 dimensions. Now, if you're memorizing equations, we've got a slew of new equations to memorize, but hopefully we'll just remember the verbal description of our fundamental definitions for kinematics, and that's the velocity is the derivative of the position, or what we call the trajectory, and the acceleration is then the derivative of the velocity. As we expand that to vector notation, then we can represent that mathematically quite easily. If I start with a position vector in time, I do the operation of differentiation on it, and I recover the velocity vector function of time. And then the same thing by doing the operation of differentiation on the velocity vector function of time, I'll get the acceleration vector of time. And so briefly, if we just sort of write this out quickly, I have a velocity, and then I'm going to differentiate the position trajectory, which has, I'll write this in component form. That has some x component that's a function of time and a y component that's a function of time. And then the I and j are the unit vectors. Then this just becomes this operation of differentiation using our rules then just acts on each of these separate functions, and we get then the operation on the x component function I hat plus the operation on the y component j hat. And so then we identify this then as the x component of the velocity, which we've seen before, we call v sub x, and then this we identify as the y component of the velocity. All right, so that's this is most really better seen with a couple examples, so I'll try to contrive a complicated trajectory here that we might practice our differentiation rules in vector form. So if I say I have a trajectory here, it has a functional form of 3t plus 4t to the fourth I hat plus, then I'm going to have an exponential e to the negative t over tau sine of omega t j hat, and here tau and omega are both constants. My velocity then, I just differentiate each one separately. So my derivative of my polynomial gives me 3 t to the 1, or then goes, the 1 comes down, then gives me t to the 0, which is just 1, plus 16 t cubed. The 4 comes down to multiply by 4 to give me 16. 4 minus 1 is 3. And so that's I hat. And now to I have to now differentiate this, and this I'll need the product rule since I have 2 functions of time, as well as the chain rule since I have e to this function negative t over tau and this function which is omega t. And so if I differentiate the first part, I get negative 1 over tau e to the negative t over tau, and then multiplied by sine omega t. And then using the product rule, I now have to differentiate sine omega t. Using the product rule gives me omega e to the negative t over tau times cosine omega t j hat. Okay, and so then if we were truly glutton for punishment, we could differentiate that again and find the acceleration. Normally, of course, we don't have the trajectory and need the velocity and the acceleration. Often what we have is the acceleration and we need to go backwards. And so let's look, just for an example, assume a constant acceleration. In vector form, what does that look like? Well, it just gives me some acceleration I hat plus some constant acceleration vector, but now it has components along the x and the y axis. Okay, so now if we want to find the velocity, now the velocity is going to be the antiderivative of the acceleration, but just like differentiation, it just becomes the antiderivative of each component, keeping them separate along the x and the y axes. So so it's just a matter of the one-dimensional case. I just have to do it for both axes separately. All right. So the antiderivative of a constant is ax times t plus another constant, and I like to call that constant v sub xo because it's on the x-axis, and I call it 0 naught here because it's going to be the velocity at v is equal to 0. And so this is my velocity. I wrote a again, but I want to do the velocity, which is the antiderivative. And so this is now the I hat. And now the antiderivative of this constant then gives me that constant times time plus another constant, and I call this constant v sub y naught because it will represent the y component of the velocity when t is equal to 0. And so now I have the velocity as a function of time. Okay, and we can do this one more time, and so I'll get the trajectory, then the antiderivative of this, which is 1/2 a sub x t. My t got out of control there. 1/2 t squared, antiderivative of this constant v sub x naught t, and plus another constant. And I call that x naught because it represents the position when t is equal to 0. And this is all along the x direction. And then plus the same thing in the y, 1/2 ay t squared plus v y naught t, and then plus another constant. It's antiderivative. I call this constant y naught because it represents the y component of the position vector when t is equal to 0. And so we notice that the procedure maps identically the one-dimensional case, but the key is in vector form that the components, all the math of the components stay separate, and so you have a set of equations for each component separately. And so that becomes an important part that we'll see when we do examples, say for constant acceleration in 2 dimensions. You keep the components separate, and you solve the equations separately, however, they're linked by time. While this is only the x position and this is the y position, which are separate components, this time is the same everywhere. And so you can establish relationships between the x and the y components through the way they share the time variable. All right. So now let's take a look at a graphical representation of this motion. So just to look at it a little bit, graphical representation. So, for example, now I have in 2 dimensions, I might have an x and a y-axis. And now I can look at my trajectory r as a function of time and imagine it looks something like this. I have some sort of projectile motion. And so we've looked at these sorts of graphs before, but remember, this is not now x versus t. These are both position vectors, y and x. So imagine if I have, let's consider here projectile motion. Now for projectile motion, we have an acceleration vector then that has 0 in the x direction. And let's give it a negative g here in the y direction. Now I'm giving, since it's a negative, I'm assuming then that I have my positive y going up. It doesn't have to be, but for this example, we'll do it that way. So in that case, this position vector has x naught plus v naught xt in the I hat, and then plus y naught plus v naught yt minus 1/2 acceleration due to gravity times the time squared in the j hat direction. And so that is represented now by this graph here as a function of x. So you can also graph, like we did before, x as a function of time. And here, if we say the velocity of x as a function of time, in this case, it has some initial velocity and it stays constant because there's no acceleration in the x direction. So the velocity of x as a function of time, the velocity is a function of time, but x is a function of time, looks like this. It starts out at 0. And so it's just going to increase linearly. And also, we can plot y as a function of time. It's going to start at some initial position, and it looks like a parabola, and so it might have some shape that looks like this. But these two graphs here are very different than this. This is showing me the actual trajectory in position space, y versus x. While these two graphs are showing me the two components, x and y, as a function of time. For example, if I look at the slope of this line, the slope of this line gives me the x component of the velocity, just like the slope of this line at any point gives me the y component of the velocity. On this graph, however, if I come up to here and look at what the slope of the tangent line at any point on this graph gives me the direction of the velocity vector. So if I go at this point, if I look at because this represents the trajectory, the trajectory of the particle as it follows, at this point in space, it has a velocity vector that's pointing along the tangent line of this curve. So given that, I can use this graph, if I give myself an axis here, I can use this graph to establish a relationship between the x and the y component of the velocity. Now, this projection of this vector on the horizontal axis is the x component of the velocity. The projection of this vector on the vertical axis is the y component of the velocity. And I can sometime then I can might be able to find this angle theta here to be able to relate the two. And so now in 2 dimensions we have another way to represent the graphical motion, and it gives us more useful information. But it's important not to confuse this graphical representation with the position versus time graphs that we were looking at before. And that's the end of this module.